Scenario 1 of ISEL, developed within the scope of the PAFSE project, is entitled Droplets and the Physics of Viruses Transmission. In relation to the science content from the scenario, the study and prediction of spread of respiratory droplets is relevant because it can mitigate the dissemination of diseases that spread by air, thus promoting a healthier life and well-being for everyone of all ages. The analysis of respiratory particle physics and its transmission process will allow students to develop methodologies for analyzing and presenting solutions and discussing and arguing facts about scientific problems, contributing to their interest in STEM-related areas, STEM being science, technology, engineering, and mathematics, and the scientific and pedagogical content of the scenario allows teachers and students to explore the prediction of airborne diseases and their relationship with public health and subsequently present action measures in their communities to mitigate the spread of such diseases. So, in this study, in this scenario, it is intended that students analyze the physics in a simple way, the physics of airborne transmission, so they can relate airborne diseases with public health issues, with public health, and subsequently produce a series of actions to be taken, both individually and community-wise, to mitigate the spread of such diseases. So this scenario contains research-based activities, learning objects, interaction with animated graphic simulator, and updated facts. The scenario also aims to prepare students and the school community to reduce the risk of airborne diseases. So this is the main theme of this scenario, and the creation of this scenario was strongly influenced by the COVID-19 pandemic, in which it is commonly accepted that in the scientific community that the virus spreads essentially through the air. And with the technological advances achieved, nowadays is possible and relevant to explore with the students a tool that allows the prediction of the propagation of airborne particles, and this tool is called computational fluid dynamics, CFD. And with this tool, students will be able, in the scenario, to predict, to analyze some videos of CFD simulations where they will see particles spreading through time in different configurations, in particles emitted in different breathing regimes. So, for example, they will see a person sneeze, coughed, or talk in different room configurations, room with or without ventilation, with natural ventilation, with tables, chairs, etc. And this will allow students to estimate the risk of transmission of respiratory diseases between individuals. So this learning scenario increases students' understanding on how the transmission of airborne diseases works and how science, technology, engineering, and mathematics can contribute to anticipate, mitigate, and solve public health issues like, for example, airborne diseases with the exploration of, in this case, a computational fluid dynamics tool. So, in terms of learning objectives that we want students to achieve at the end of the scenario, in this specific scenario, we want students to describe in a global way, in a simple way, the physical process of propagation of airborne droplets and the respective conditioning factors. We will also want students to obtain and evaluate data and scientific basis on diseases that spread through air and use facts to argue about the process of transmitting virus by air. We will also want students to be able to use computational tools to build tables, graphics, and other data that aid in the understanding of the physical process behind the propagation of respiratory droplets. And we will also want students to provide examples of factors influencing the spread of airborne viruses and identifying general measures and actions to combat the spreading of such diseases. In terms of the scenario structure, The scenario is constructed to be implemented in six classes of 40 to 45 minutes and a variable number of extra sections for students to develop their school's research project, which will be the output of this project, and we will talk about it later in this video. And the teacher deepens or selects specific topics according to students' prior knowledge, school curriculum, and time constraints, which means that the scenario is conceived to be implemented in six classes, but in the school's research project to be addressed in 4 to 6 sessions, but um, the project can be implemented in more or less lessons. This will all depend on the teacher's time constraints, the student's prior knowledge to the subject, and so the time that the project will last is up for professors' decisions. From classes 1 to 6, students work alone or in groups depending on the activity. And to carry out the school research project, students should be divided into groups of 4 to 5 students. It will be necessary to use the computer or mobile phone, and students will be required to know or have basic knowledge of Word or PowerPoint, as well as basic knowledge of English. In terms of class planning, we have a certain space reserved for the first class where the teacher presents the PAFSE project, the learning objectives, and what the students will be doing in the future regarding the project, and then the professor will address the introductory concepts related to the physics of airborne diseases. And this will all be addressed with the aid of the learning resources available at the PAFS project that the teachers will have access to. And then at class 2, they will consolidate the concepts that they previously were introduced in class 1, and those are the concepts of physics of airborne viruses transmission. In these two classes will serve as theoretical classes, so students have the basic knowledge, so they can then analyze in classes 3 and 4 the CFD simulation videos, where they will see the particles spreading through time, uh, being emitted at different breathing regimes. A regime where a person coughs, another talks, and another sneezes at different room configurations. And they will do it by analyzing CFD simulations of an initial case study in class 3, a small room with a few elements and very simple geometries, so they can analyze how particles is spreading through air. And then in class 4 they will analyze more complex case studies, and where they will then make a comparison between what they observe in cases of the classes 4 and the cases of class 3. And then in class 5, the students will present the main factors, the main conclusions that they obtain regarding airborne transmission by the visualization of the videos of classes 3 and 4, and they will debate the results obtained in the analysis of such simulations, and they will conclude several measures that they think that can be taken both individually and at community-wise to mitigate the spread of such airborne diseases based, like I said, the knowledge that they acquired from classes 1 to 2 and the visualization of the videos in class 3 and 4. And then in class 6, it is reserved a certain amount of time to conclude class 5 and to discuss the school research project. And basically, based on the knowledge acquired in the previous classes, in the school research project, the students are encouraged to revisit the scientific articles they consulted in their research process to explain the results of the simulations, and also, based on this information, to elaborate their proposals to improve public health. And these proposals will be presented in the form of a poster or scientific information. So the project should be carried out in groups, preferably the groups formed in classes that implemented all the activities of the scenario. And we also want the project to be multidisciplinary. That is, besides the professor that is coordinating the project, The other professors, such as, for example, arts teacher, can help students in design and creativity of the scientific poster. The ICT teacher can help students with the creation of the scientific presentation. And, for example, the Portuguese and English teacher, the language teachers, can help in the proofreading of texts, producing both outputs, that is, the scientific presentation and the poster.